Bases do the same thing. NaOH is considered a strong base. The strong bases are the 5 metals in the left-hand column: lithium, sodium, potassium, cesium, rubidium. Francium, if you want to include that, that's fine, but it's man-made. And then the bottom half of the second column, which is strontium, barium, and radium. So, if we have sodium hydroxide, that is in group 1A metal, it is not going to break down double arrow. I'm sorry, it's strong. It's going to be 100%, so that will be a single arrow, and that will give you Na positive aqueous plus OH negative aqueous. Okay? And then if you had like copper 1 hydroxide, which looks like this is not one of the 9. It's not found in group 1 or group 2. And so this is going to be double arrow. But the products will look pretty similar, except that the products actually is a mixture of what we see here as products and this stuff here. That's why the double arrow exists. So we expect the pH for this to be, if we had equal concentrations of these two, you would expect the pH of this to be higher than of this. Now, we'll talk about pH, which we'll get into in just a little bit. The pH is determined by the hydrogen ion that is available in the acids, and it's determined by the hydroxide ions in the bases. Okay? So, that brings us down here to the last statement I have. And that is the fact that Arrhenius is the guy who kicked off everything about acids and bases that is taught in most of the lower level schools, like middle school and lower high school freshmen. And he found, and remember when we talked about equilibrium systems, when you have a double arrow reaction, you're going to get a K value. And since water is considered a weak acid or a weak base, and I'll show you in just a minute what that means, it's going to have a K value, and that K value he found to be 1 times 10 to the negative 14. And that equals the concentration of hydrogen times the concentration of hydroxide. Why? Let's find out. So here's water. Like I said, water is considered both a weak acid and a weak base. Compounds that do that, alcohols do that as well, they are amphoteric. That means both acidic and basic. Both the hydrogen can come off and the hydroxide can come off. So we use a double arrow because it's not a full-fledged strong acid or a full-fledged strong base. But we treat it as hydrogen hydroxide, not H2O. We talked about that in organic. So this will be H positive aqueous plus OH negative aqueous. Okay? So that means there's a K value for this. K is equal to concentration of hydrogen times the concentration of hydroxide. But we don't put water there because that's a liquid. So that's all we can have in there. And like I said, Arrhenius found this value to be 1 times 10 to the negative 14. Okay? He called this KW. We have Ka for acid or acidic solutions, Kb for basic solutions, Kc for concentrations, Kp for pressures. This is Kw for water. And under all these conditions, it will always be 1 times 10 to the negative 14. Right? You can say these conditions we're talking about standard. 1 atmosphere pressure, and 0 degrees or STP. So let's suppose that we have a 0.10 molar solution of HCl. And I want to know what the pH is for this, based upon this right here. Okay? Now, 0.10 molar means it's 0.10 moles per 1 liter of solution. Now, I can find the pH. I can also find the concentration of hydrogen, and I can find the concentration of OH, because they are actually all related. Now, we haven't talked about pH yet, so I'll come back to that. But I'm going to deal with these two right here. All right? If this is 0.10 molar, okay, that means then that let's take a look at HCl as an example. Single arrow, 0.10 molar, gives you H positive aqueous plus Cl negative aqueous. So when this breaks down using stoichiometry 1 to 1 to 1, this is 0.10 molar and this is 0.10 molar. Well, we don't care about the chloride because it doesn't really have an effect upon anything, but this gives us our concentration of hydrogen ions. So I'll put this as 0.10 molar. Hydroxide, now, because this is dissolved in water, that's what aqueous means, dissolved in water, there's water involved in this reaction right here, the aqueous. So that means there has to be some OH to allow this value of 1 times 10 to the negative 14 to exist in any water solution. So if you dump a whole buttload of hydrogen ions in there, you're going to decrease the OH negative, but you're never going to get rid of it completely. So there's a hint of hydroxide in the solution. How much? Well, we go back. Concentration of hydrogen times the concentration of chloride equals 1 times 10 to the negative 14. So I replace this as 0.10. Divide both sides by 0.10. And the concentration of, oh, shoot. I'm sorry, that's supposed to be OH right there. Using the water one, not the HCl one. The water is the one that has the 1 times 10 to the negative 14. So, divide by 0.10, that's going to leave me concentration of hydroxide. You divide that out, get 1 times 10 to the negative 13 moles per liter. Now, pH. H stands for the concentration of hydrogen. P is a mathematical process. And it is short for the negative logarithm base 10 of this value. So this is a negative log of the concentration of hydrogen. Well, we know that the concentration of hydrogen is 0.10 here. So this is going to equal to the negative log of 0.10. You punch that into your calculator, you get 1. Why? Because this is 10 to the negative 1 power. And negative log means negative exponent base 10, that's base 10, so the negative exponent is the negative of a negative 1, which is positive 1. Now you can leave it as 1, I don't care. But don't put a label on it. There is no label for pH. If I have a concentration of sodium hydroxide of let's say 0.001 mole per liter, I want to know what is the concentration of hydroxide. I want to know what is the concentration of hydrogen. And I want to know what the pH of that solution is. Okay? So, well, sodium hydroxide is strong. So that means that NaOH, when dissolved in water, is a single arrow reaction, creating all the sodium you can get out of that and all the hydroxide you can get out of that. Alright? So, if this is 0.001, and this is a single arrow, it means the stoichiometry is going to break this down completely. This is 0.001 moles per liter, which we don't care because that's not going to change the pH at all. But this is where the pH comes into play. 0.001 molar of this hydroxide. So yes, every time the H positive and the Cl and the OH negative from a strong or weak acid will be exactly the same concentration as what you're given in the problem. Every time. Now the hydrogen, since we know that 1 times 10 to the negative 14 is equal to hydrogen times hydroxide, we can rewrite this so that hydrogen is by itself by dividing by the hydroxide concentration. So the hydrogen ion concentration is going to equal to 1 times 10 to the negative 14 divided by the concentration of hydroxide, which in this case is 0.001. And you divide this out, and you get 1 times 10 to the negative 11th moles per liter of hydrogen ions. So, right there, we put 1 times 10 to the negative 11th moles per liter. pH then is the negative log of hydrogen, not hydroxide. So we use that value right there and we get 11 as my pH. And because it's greater than 7, that tells us we are dealing with a basic solution, as we expect. Now, one more thing I want to talk about here real quick deals with numbers that aren't really nice and neat numbers for our concentration. So let's suppose we have a 0.477 molar solution of HClO4. And I want to know what is the concentration of hydrogen, what is the concentration of hydroxide, and what is the pH of this solution. That's what we're trying to find here. Okay? So, for this, we are going to find that this is a strong acid, which means the concentration can be what this is right here for hydrogen. So that's 0.477 molar. We know that hydroxide, just like it was for the other, 1 times 10 to the negative 14 over the concentration of hydrogen, which we said is 0.477. So we go to our calculators, and now we really start using our calculator. And we get 1e negative 14 divided by 0.477. And we get 2.10 times 10 to the negative 14 molar. And those are concentrations, so you have to put the capital M on there. You will get it back if you don't do it. pH is the negative log of the hydrogen. Well, the hydrogen here is 0.477. So negative log 0.477 is 0.321 molar. Now, I'm going to stop right there. There's still something about dealing with pH and finding concentration for that. We're not going to do that today. I want you to get used to doing this. So, yeah. So, 5 practice problems at the end of the script. Have fun.